Okay, so all right. So if reaction takes place at 200 degrees Celsius and the NO concentration is 0.045 moles per liter, the O2 concentration is 0.11 moles per liter, and the NO2 concentration is equal to 12.5 moles per liter. Calculate Kc. And Kp. And then comment on the feasibility. I don't know if I'm going to spell that right.
If you can't spell it, then you can't write it.
That's not true.
So we can't do it.
Feasible is spelled that with an E, so I think that's feasibility. You could say plausibility. Like, is this reaction plausible? What that means in chemistry is, what's the point? You want to make nitrogen dioxide. So after you do all this, are you going to make a lot of nitrogen dioxide? That's what that means. How does that relate to what we're learning? If K is much bigger than 1, that means you're going to make a lot of products. So that would be feasible. So, I'm going to give you a little time here. Take the information, solve for Kp and Kc. Kp can't come directly from these numbers because they're not pressure. But Kc can, then you use that equation. Surprised someone hasn't asked me yet. Thank you.
Change in moles.
Oh, good. Change in moles. Where does that come from?
From the left and the right. Add the left.
It's 2 and 1, so you have 3 moles of reactants and 2 moles of product. So in this example here, it's always products minus reactants. So here, I'll write this. So delta N is your products minus reactants in terms of moles. So it's going to be 2 minus 3, which is -1. So the delta N for this one, I'll just tell you, is going to be -1. So it's 2 minus 3, so -1. All right, go ahead. You got everything you need. Feel free to work with somebody or talk to somebody, and then we'll go over it. Who doesn't know how to start? Fair enough. Okay, so you would start with Kc equals the products raised to 2, and then the reactants raised to the second and raised to the first. So this one raised to the second divided by this one raised to the second, or squared, and then this one raised to the first power. Plug in the numbers, solve for Kc. Then use that other equation with the delta N here to solve for Kp. Does that help? Okay. The number for Kc is enormous, if that helps.
Right. Yeah.
It's because you're doing 12.5 squared. That's a big number.
you're dividing it by a really
and you're
small
dividing by a really tiny number, right? So, Trevor seems to be on board here, hopefully everybody else is. Yeah, I just want to see your number for KC when I'm coming around here. Or at least session out.
You could change the temperature to Kelvin or can you leave it Celsius?
That, my friend,
Do not. We do everything in
No.
Kelvin.
is the question.
So it's Kelvin.
That is the key to one-eyed Willie.
What if frozen in?
It's Kelvin.
Oh, I'll
Yes,
frozen.
no. Or some-
I know, just so difficult sometimes, sorry. Just,
Really good.
Comment on the, wait, what does feasibility mean again?
how feasible is the reaction? Does it make sense to do this? Are you gonna make a lot of products?
This time.
Alright. Do we have answers?
Yeah.
Alright, KC is 7 times 10 to the 5th, if I round it. 7.01 times 10 to the 5th. And then KP is 1.81 times 10 to the 4th.
What's like, what do you write for the unit?
It doesn't have one.
No unit on either of them?
Right, 'cause they should cancel out. Alright. So, these numbers are way bigger than 1. So what does that mean? Favor products. Favor products. Okay, good. Alright, now, another question for you guys. Let's say this reaction is flipped. So do I need to show how to do that? Who wants me to go over it? I don't really want to.
Yeah.
Okay, alright.
I don't know what you.
Okay. Alright,
Wait, was it?
so,
Wait, was it feasible?
yeah, it's feasible.
Okay.
Big time. The larger this number, the more feasible it is to make products, and that's what the goal of all reactions are. You don't do reactions to make reactants. You already have them. So that's what it means by feasible. All right. So the setup here would be, where's NO2 here? 12.5 squared divided by 0.045 squared times 0.11. When you do that, you get 7.01 times 10 to the 5th. That's for Kc. So now, to solve for Kp, we use that other equation. Kp equals 7.01 times 10 to the 5th times 0.0821 times 473 Kelvin raised to the negative 1. So 0.0821 times 473 raised to the negative 1 times this number is 1.81 times 10 to the 4th.
Can you write out the whole number and have, is it better to put it in?
Oh, it doesn't matter. Technically, you should, pay attention to sig figs. They all have, this has 2, so that's screwed up. Usually 3. 3 is a good number. 3 sig figs is a good number for answers. So 7.01, 1.81 times 10 to the 4th.
Well, if you had something wrong,
I can't remember seeing a question that specified that. Just don't, always have more than less. In other words, if you write out the whole thing and it doesn't say anything about rounding or sig figs, then you're fine. Does that help?
Yeah.
No one's gonna mark you off for that. Again, the guy who gave that workshop a few years ago, I keep talking about, he said the graders, the readers, they're called, as long as you're showing good chemistry, it's kind of a cheesy phrase, but what that means, if you're showing you know what to do and you're showing everything correctly, they're not gonna, if you wrote 7.0 times 10 to the 5th and left the 1 off, they're not gonna take points off. That's unless it specifies. Alright. Okay, so there's that. What if I flip the reaction? So, yes, I know it's reversible and it's at equilibrium, but so if we write it the opposite way, so 2 NO gas plus 2 NO gas plus,
wait, isn't it 2 and 02? Yeah.
sorry, 2 NO2. All right, so there's the reaction. Now rewrite it, flip it though, write that. Tell me, what is the value of Kc and Kp? Everything's the same 200 degrees, but now this is how it's written.
Are we like solving for it?
Yeah, solve for Kc, everything's exactly the same. Just solve for Kc, solve for Kp again. But I'm going to give you a hint. You don't have to do products over reactants. You can, but there's a quicker way to do it. Okay, look at the board, see if it makes sense to you. So KC, the one on the left, was the first problem again. KC prime, just to tell the difference between the two, is for the reverse, right? So if we flip the reaction and we write it that way, so what we're currently doing, you can just do that calculation on the bottom. You don't need to do products over reactants. You can just do 1 over the original one. Why does that make sense? Right, so what's 1 over mean? In math. Give me a word for that. Inverse. Inverse, right?
Yeah.
So if you flip it, you're taking the inverse of that equilibrium constant. So if you know the K value for one direction, the way that is set up on paper or in the book, a test or whatever, and then it's given to you the other way, you just take 1 over that original number. Why is that useful? You're going to see if they give you a reaction, let me say this differently. Yeah, they give you a reaction and they give you an equilibrium constant, but then the question is involving the reverse of that reaction, you're still expected to know how to get that number even if they don't give you the individual concentrations. In other words, if I tell you this is 7.01 times 10 to the 5th, and then on an AP test, they give you this reaction. They don't give you the concentrations, and they ask, okay, what is Kp? So they give you this reaction, that first one, they give you the value of K, then they say, okay, now the reaction's flipped, what's the value of Kp? So they don't give you the individual concentrations. You're expected to know if I have this one and it's reversed, I can just take the inverse of that number and that gives me Kc, then I can use the other equation to get Kp. Are you following my logic? I'm just trying to help you out for like a test question. Yes, I want you to understand the concept. Products over reactants, that's how you get K, but it's going to be more complicated. They're not always going to give these to you. They're going to give you one of them and then flip it, and then you have to figure out what all the other numbers are. So for this one, it's just notes and we're practicing. So if you took the concentrations and calculated it out, it is the exact same of taking 1 over this number. So either way, when you do that, what do you guys get? Do you get 1.43 times 10 to the negative 6?
Yep.
Okay, good. So yeah, if we take 1 over 7.01 times 10 to the 5th, we get 1.43 times 10 to the negative 6. So that's going to be our Kc prime. Then we plug that number in to find Kp. So 1.43 times 10 to the negative 6 times 0.0821 times 473. Now this time it's 3 minus 2, so that's positive 1, right? Your delta n is different because it's reversed. So it's 3 minus 2. So this calculation for Kp is 5.54 times 10 to the negative 5th. 5.54 times 10 to the negative 5th. That's for Kp. Kp, I guess we could say prime, but everybody with me? Okay, which reaction is more feasible? First one or this one? First one. What does this favor? Reactants. You don't do reactions to make reactants. That doesn't make sense, right? So that's 2 good examples of how to solve for both of those. The relationship if you flip. All right. How to set these up. Which direction's favored. So you're learning a lot here today. Hope you're with me. All right. I'm gonna use all the time we have here. All right. So if you need to write this down, you can. Liquids, solids don't go in these calculations here. Liquids and solids don't go in the calculation because changes in those. The better way to say it is, so like water, solid calcium carbonate, or solid baking soda. If you have liquids or solids, there's such an overwhelming number of moles of them already that if you do little changes to them, it doesn't really affect it. Gases, like these, in concentrations of solutions, so aqueous, little changes make a big change in the equilibrium. But if you have a solution in water, for example, it's not the water that's really affecting it; it's the stuff dissolved in the water. So I'm trying to make sense to just help you remember that. But solids and liquids, you'll never see in here. Only aqueous and gases. Okay, I didn't tell you that before the homework, so it was probably pretty tricky. This does get a little confusing if you're given an equation, actually like that homework problem. Let me use this as an example. So, where was it? So, if you have this, write this in your notes. I'm going to give you two examples where this can confuse you if you don't remember solids and liquids don't belong. So, CaCO3, the decomposition of CaCO3 solid, you get calcium oxide and carbon dioxide. So go ahead and write that down. If you want to solve any sort of equilibrium expression using this reaction, these two don't belong. So the Kc for this equation would be the concentration of CO2, period. That's it. And the Kp would be the partial pressure of the CO2. That's it. Only the partial pressure or concentration of the carbon dioxide affects this equilibrium. These two don't. And again, it's because there's already an overwhelming number of moles of solid involved. Little changes to these doesn't really affect much. And it won't affect the volume of the container or the pressure this gas feels. So, I know I'm going quick. I'm saying things quick because I feel like this is a kind of a minor detail, but it's a huge deal writing these. So, I'm kind of contradicting myself. But if you can just remember solids and liquids don't belong, I'm good with that. All right? It's just I don't want you trying to solve for these things when you can't. So it's just gases or aqueous. Another example. AgCl solid. If we put that in water, we dissolve it in water, and it dissociates. You get Ag plus and Cl minus. If you were given this equation and they said, all right, what is the equilibrium expression? You would say, all right, K is equal to the concentration of Ag plus times the concentration of Cl minus, products over reactants. Well, this reactant's a solid, so it doesn't belong. So it's just another example. Yes, that's part of the equation, but that doesn't factor in the equilibrium expression because it's a solid. If there was water in here, if it was AgCl plus, hold on. Go ahead.
So if it's aqueous, it still works?
Yes, because the aqueous is dependent upon the particle concentration. That is a big change. The solid and the liquid won't affect it. The number of particles actually dissolved affects it, not the solid that isn't. So if this was AgCl plus H2O, neither one of these would be in your equilibrium expression. It would just be aqueous or gas. Okay. Again, I should have told you that before the homework. One more. See what you got here. One more. Write the expression for this one. And then I'm going to introduce one thing here before I get out of here.
You have 2 minutes.
3. I'm going to use
That doesn't mean it. P4?
P4.
Oh, P4.
Okay. If you get this right, Tristan will do 25 push-ups.
All right.
What are we doing?
Writing the equilibrium expression. So K equals.
So we're finding K?
Oh, not finding it, setting any numbers.
Oh, never mind.
You're just setting up the expression.
Yeah.
Just set it up. Products over reactants. But remember, solids and liquids don't belong. Whose idea was it for the best one?
What? No, like front. Hunters? It was me, Cheyenne, Luke, Skylar, Taryn.
What are you guys, all like officers or whatever? We used to do this all the time. Last time we played against Fly Night too.
Was it fun?
It was fun. We won too. It was a really good game. They came out, they were beating us, and came back and beat. It was a good game. It was fun.
Wait, for what?
There was a lot of kids here. It was a good time. I had
Really
fun.
good.
Huh?
Really good.
Yeah, I used to be pretty good. I haven't played in years because I hurt my ankle. But I played after camp with some of the guys. Did okay.
Is that it? Over the summer?
Yeah, I played with Zach and all that. I can hold my own. Oh, Tristan, looks like you're doing push-ups. Liz got it.
Oh, wait, yeah, Friday.
I'm just gonna do it. I'm just
You
gonna.
can, I don't know, you like that. Hey, Garmin.
Where's the managee sit? Experience.
Because in the. Because in the.
How about your stuff? You're a nice person. Okay, here we go. Now, this and this does not belong, right? So it would be K equals 1 over. Now, if it was partial pressure, it would be partial pressure of Cl2 to the 6. If it was concentration, it would be brackets raised to the 6. That's a tough one.